Hello, my name is Kalman Reti, and this is a recreation of my solving of the second day of Advent of Code 2023. I did this, it's a recreation because I did it in bed under the covers on my Termux Android Emacs on a tablet. But that was in the wee hours of the morning. This is the same version of Emacs, but on a Windows 10 machine. So Advent, I'm also doing it on a second account, so it doesn't show up as already solved. Um, so here's the problem. I'm gonna start up an Emacs. Thought I had it already started. And I have already made a template for this day. Basically, this is where I'm going to stick my input. This is where I would stick sample input. If there's separate sample 2 input, part 2 input, I stick it here. And I'm going to insert the code for doing part 1 here and insert the code for doing part 1 there. And then these are the expressions to test my values, test, my this function. So what is the problem? Well, Santa's landed on this snow island, but there's no snow. And the elf who's guiding him needs to have him walk a long distance, so they play a game along the way. The game consists of the elf putting in some unknown number of red, green, and blue cubes into a bag. And then Santa has to try to get information about how many there are. And the elf will randomly pick out a subset and show him. So he'll do it a few times. So each game is listed like this. So there's a game number, and then there's going to be several subsets of the cubes in the bag. So this first one is 3 blue and 4 red. And so the elf and Santa's keeping track of all of these, and that's the same as the puzzle input. So this is going to be my sample input. I'm going to copy this and put it here as part 1 sample. Uh, Control meta E goes to the end of an expression. Lisp has a whole hierarchy of commands like Control F goes forward a character, Control B goes backwards a character, but meta F goes forward a word and meta B goes backwards a word, and Control meta F goes forward a whole expression and Control meta B goes backwards a whole expression. Control meta U goes upwards in expression. So if you're inside some parentheses, it'll go up a level. Control meta A goes to the beginning of the definition. Control meta E goes to the end. And so I can go to the end of a definition. Control X, Control E will evaluate the expression that's before the cursor. So if you go to the end of an expression and then type Control X, Control E, that will actually define, evaluate that expression inside of the Lisp environment. So I just did that for this defvar or the sample. Um, so what the elf is wanting to know, and the answer for the part 1 is they were playing this game, but if the elf had restricted himself to only 12 red cubes, 13 green cubes, and 14 blue cubes, which would have of this list of games would have been possible? Well, you couldn't have done game 3 because this one of the times got 20 red cubes and there wouldn't have been 20 red cubes. And similarly, this one wouldn't have been possible um, because it got 15 blue cubes and there would have only been 14 blue cubes. So what they want to do is of all of the games that were played and recorded, they want you to add up the IDs of the ones that were possible. So this would have been 1, 2, and 5, which is 8. So that's the function we have to write. So this is mostly going to be parsing this time. That's not unusual. So loop with limits equals list of 12, 13, 14. We know there's only red, green, and blue. We're going to use the canonical ordering. So this is the list of limits that we're interested in. So the input string that comes in is the entire input. Oh, I should actually go get that. So here, let's go back and get our puzzle input and go back. No, I don't want that. Then with that, and go up to the top here and put that in as my input and Control Meta E to go to the end, Control X, Control E to evaluate it. Notice at the bottom it told me that the definition of the input variable is there. And so we can go back to doing the for a game. And now we want a list of the separate lines so that we can get that with split string. Notice at the bottom it tells us the arguments. So input string is the string that we're splitting, and what we'll get back is a list of substrings, uh, namely the things that are between the delimiters. In this case, the delimiter I want is new line. So so we're going to use a regular expression to split off um, the different pieces of this one game. The first part is the game, you know, number colon. The emacs has a bunch of regular expressions: search forward regex, search forward back, search backward regex. Run on the buffer and move the cursor, but match string uses regex on a string that you supply. So except it's called string match. Match string is the other one. So string match uses a regex. So we need game. We need a group. Uh, a regex uses backslash, but that's the quoting character inside of a string in Lisp. So we have to have two of them to get one inside the string. Uh, and what we want is some number of digits, at least one. That's the plus. Colon space. And then we're going to use the whole rest of the thing dot plus and dollar to say go to the end. So that's the regular expression. It's going to give us two groups, um, the ID number string and the stuff after the colon string. And we're going to use that on the string game. Now, pause is going to be the index where it matched, which should be 0. In fact, we could check that and error out if it wasn't 0. But if it doesn't find a match, it's going to be nil. So for now, what we need is we need the actual ID. And that would be the contents of that first group, but it's a string, so we're going to turn it into a number. So this is not going to work until I evaluate these guys. So in my template here, I have these two expressions: require CL, which brings in the common list compatibility package, and set debug on quit to true with T, a true value. The only false value in Lisp is nil. Anything else is true, but there's a canonical truth value called T. The reason T and nil are special is that they are, unlike all the other symbols in Lisp, not movable by the garbage collector. And so testing for them is basically a pointer comparison against a fixed address, one fixed address for nil and one fixed address for T. So it's very, very efficient. Anyway, one of the things you get with the require CL is a whole bunch of common Lisp functions. Loop, the macro itself is a common Lisp macro. So match string is what you use to get the contents of one of the groups. You want the group number, and since I use it against the string rather than the buffer, I have to actually supply the string I used it against. So that's going to get me the ID. And then what I want is, because we want to see whether the game that we got is possible, we want to collect up the max number of any different color that we've gotten. So I'm going to say maxes, namely a list of the various red, green, and blue in that order, maxes. And so we're going to loop with a local max for turn. This is one of the things, that those are separated by semicolons in, and this one is match string 2 of game, but we want a split string, and this is separated by semicolons. So this is going to be, like the 1 blue comma 2 green semicolon, turn of the game. Do, and we're going to loop again, but this time for color string in split string of turn by comma. So this color string has the number and the color. So 1 blue, 2 green, 3 green, that sort of thing. And we're going to say that the N string and the C string are equal to split string of color string. The default delimiter is white space, so that'll split across the space that separates them. And for N equals CL parse integer of N string, so that gets us N as a number. And the index we want to update our max list that we have with at the beginning of this loop is index equals position of color C string in red, green, blue. We used to have to test with equal, otherwise we'd be testing the pointer equality, which wouldn't work for strings. And then, so that's going to give us the index in our list that we're keeping as max for this particular color. And so when n is greater than the nth index of max, in other words, this particular turn has a larger number of this particular color, setf. Now setf is a cool macro because it takes you a getter expression and turns it into the setter expression behind your back without you having to know what that is. And moreover, it could be an arbitrarily complicated expression. So you can be getting the nth thing of a struct that has an accessor, which then is the nth thing of some other struct, as many levels down as you want. So we're going to update it as long as it's greater. We're going to update it, and we started out with 0, so it's the first one will be greater. And so this inner loop here inside the do just updated max. And so all we're going to do from the outer loop is return max. So that's going to be the RJB that we've got. And to be able to use those individually, okay, well, we probably don't need them, but we can do this. MR, MG, MB equals maxes. What that's going to do is it's going to set the variables MR, MG, and MB as the 3 elements of the list maxes. So the real thing we want to know, is this possible? this game that we're that's this iteration of this loop, and it's possible loop if loop for m in maxes for L in limit always less than or equal to ML. Namely, for all of the maxes of the particular color, are they all only as much as the limit? Um, and if that's true, we'll get back true. Um, so, so all we have to do is basically sum when possible, sum ID, because they just want us to tell us the ones that are possible. So I just defined that function, went down here. I'm going to get this as an expression. If you type Control U before metacolon, then the answer will be inserted into the buffer of. So I was saying of out loud, and I put it in the constant. Again, a single keystroke to get and another keystroke to compile it. Uh, Go back to here. Limit. It's called limits. Well, somehow it lost the position. I don't know. So 8 is in fact the answer that they told us in the problem here that you'd get on the sample. So let's now do it on our real input. Pretty sure we defined that input, but in case we didn't, sorry, I didn't do the trick of inserting it into the buffer. So 2105 is the answer for this set of input. We'll put it in and say submit. And in fact, that works. So the second is that the ELF poses the second question. In each game you played, what is the fewest number of cubes of each color that could have been in the bag to make the game possible? So that is in fact just the max that we found, which we were comparing against the limits to decide to see if it's possible. And they're saying that the power of a set of cubes is equal to the numbers of red, green, and blue cubes multiplied together. And so the power of the minimum set of cubes in game 1 is 48. In games 2 through 5, it was 12, 15, 630, and 36. And then so adding all of them together, it gets 2286 on the sample problem. So many times, and in this case, you can just add an optional argument to do part 2 as part of the same thing. And after we've done that, what we can do is we can just input string t. So the part 2 definition is just calling the first one with an extra argument of t. And so for possible, so what we really want to sum is a different thing. What we want to sum here is so and moreover, we want to sum it for all of them, not only when it's possible. So when or part 2 possible. So that means that if part 2 is true, i.e. we're doing part 2, we're going to do the summing each time. But if part 2 is not true, namely we're doing pot wall, then we're only going to do the summing for part one. And what we're going to sum is if part two, we have to just multiply all the things. So apply the multiply function to maxes. That's the list of its arguments. And that's it. That's a pretty smallish change. So first we want to make sure that we haven't broken part one. So Control X, Control E, oops, part one. Part two, did I spell part two wrong? Yeah, I did. Okay, so um, so doing it with no extra argument, part one still gives us the same answers. Oops. So we don't have a separate part two sample, so I'd have to change this to part one. And 2286, that's exactly what they got. So then we're going to do this guy. And it's 72, 422. Let's see. And indeed, we got the right answer. So that was day two. This is a little longer than I wanted it to be, but thanks for your attention.